Thanks to Squarespace for sponsoring this video. If you need a website, go to squarespace.com/JamesBruton for 10% off. Recently, I did a project to build a real transformer that you might have seen in my channel. You should check out the build series and the 2 reveal videos we did where we pranked the public in a garage. Now that was a fairly big machine, some of it was steel, some of it was wood, and we used pneumatics to drive that project. So I've got one of the cylinders here. In fact, there were 4 cylinders in that build, 2 bigger ones than this, and 2 like this, and these are 63mm bore. This one's 500mm stroke, and we had 2 900s as well. Now 120 psi, which is about 8 bar, a cylinder like this can drive about 300 kilograms of force, which is a lot. So I don't normally do much pneumatics in projects. Normally I use electric actuators for various reasons I'll come on to. But I really like the project, and I really like the force we could convey with these, basically, versus the cost, because they're quite cheap relatively. So I quite like to do some more projects, maybe to build another giant robot that can actually walk along on 2 legs, like a giant rock monster perhaps, or another exosuit that I can walk in, perhaps more like an alien's power loader. So today I'm going to look at how we can drive pneumatic cylinders better, and talk about some of the pros and cons between this and electric actuators that I use in other robots. So the main reason I don't use pneumatics a lot in projects is, of course, we need to drive it with compressed air. So to get compressed air, we need an air compressor. So I've got a compressor here, it's only a little one, but it weighs quite a bit. It's got a 24 litre tank, and I've also got another air receiver tank here that I can charge up that's just the tank, which obviously doesn't have the motor on, so that's significantly lighter. But it's also massive, and you'll notice that the cylinder, for this size cylinder at least, relative to its size, this doesn't fit in here a lot of times mainly, so that means you don't get many goes. Probably 2 or 3 or something at full compression out of a tank like this to push this up once at 120 psi and still maintain the force. So in the transformer build, in order to transform it once, we used all the air in this one, which is a 24 litre tank, and all the air in this one. And then in between transformations, we had to charge this up from the compressor, charge the compressor up, and then start again. So obviously the compressor is outlet powered. It weighs quite a bit. It's not really a thing you could put on a portable robot. You'd have to have one with an engine or something if you wanted to do that. So basically that's not that efficient. And of course, if I filled up one of these tanks with batteries, like this LiPo that I use in OpenDog and other projects, if I completely stack the tank full of equivalent capacity, I'd have far more power, both in current drain and also in, actual capacity. So storing compressed air is quite an inefficient way to do storing energy compared to batteries. But obviously the batteries would cost so much more if I had that many LiPos, and the electric actuators as well would cost a lot more than this, because it's just a cylinder of air with a ram. Also with electric actuators like the ones in OpenDog, with far more accurate positioning. So these motors are brushless motors driven by the O drive. They've got encoders on with 8,192 counts per motor revolution, a 2:1 ratio onto a ball screw, and every revolution of the ball screw drives 5mm. So I can get incredibly good resolution on those actuators, and quite a lot of power, because they'll do up to 2 kilowatts, those motors, and the O drive is more than capable of driving them at 50 volts. In fact, it drives 2 motors with 1 board. So the problem with these is, of course, the air compresses, so I can just put my finger on there and I can still pull this. So basically it's not going to be very accurate at positioning. It'll be slightly better at higher pressure, but trying to accurately position this is very difficult. And the other issue is, of course, trying to do acceleration or deceleration curves would mean having proportional valves, but they'd still be very sloppy under load. So basically the electric actuators are far more accurate, and we can do nice motion curves. So of course cylinders like this do have their uses, and they're really good in terms of power to cost ratio. So in the actual build for the transformer, we just basically push them from one end to the other, and obviously they stop at some point, but that's okay. But if I wanted to make a walking robot or something, it would be good to have more accurate positioning. So today we're going to try and solve some of the issues. You can of course get smaller pneumatic cylinders like this one. This one still costs £40 in money though, and it's tiny. It's got tapped M5 things to let the air in and out. So that's okay, I guess, for some things. Probably repeatability, if you had a machine doing this all day, every day, 24 hours a day in an exhibition or something, probably lasts quite a long time. But for the power you can exert on this, you might as well have a ball screw and a nice brushless motor, which gives you all the other advantages. I should also mention there's another type of actuator called an air muscle, which is one of these, and this has got a piece of tube in the middle that expands, and as it does so, it pulls in, and these can exert quite a lot of force. I think this one can pull about 20 kilograms. The air goes in there, obviously it only pulls, it doesn't push as well. So these are quite good for compliant robots because it's stretchy. So that means you can have something that can comply and you can push it back, a bit like the elastic tendon robot leg that I did last week. but these are actually quite costly. You can make them yourself. So I just wanted to mention those, but really what I want to do is something that conveys much more force. So let's think about how this works. Obviously we put air in at this end and let it out of this end, it's going to push the cylinder that way, and if we put it in at this end and let it out of that end, it's going to pull it back in again. Now of course inside, attached to this bar, is a kind of stopper, and there's an empty cylinder, and of course that stopper gets pushed either way. And that means, interestingly enough, there's more force pushing out than there is pulling in, because some of the capacity when we're pulling in is used up by this bar. So this is empty cylinder, and this is empty minus this bit of capacity, so we get more force pushing in one direction than the other. And normally what we do is we'd have some solenoid valves like this to let air in or let air out. So basically they've got a pressure, a release and an actuator connector. The actuator connector goes onto the actuator, pressure comes from your compressor or your air reservoir, and when you activate them it puts air in. When you deactivate them, air comes out here extremely fast. So basically, if we were just to basically put air in here or in here, switch on one valve or the other, it's going to go really, really fast till it gets to the end, or really, really fast till it gets to the other end, using air straight out of the compressor. So that makes it very hard to position, and even if we did, there's going to be far more compressed air in one end of the cylinder than there is in the other, so it's likely just to creep, and depending on what the load is, that's going to make it really spongy and inaccurate. So ideally what we want is a system where we can pressurise both halves of the cylinder and adjust the amount of compressed air in there to sort of hold it in position. But first of all, we're going to need some way of actually measuring the position. This isn't attached to anything. I can't get a slide pot that's 500mm long, so I'm going to make something that fits on here so I can measure the position, read that of an Arduino, and then work out how to activate these valves. Right, we've attached some 3D printed bits and pieces to it, look at that. So now we can track the position. So let's have a closer look at what we've got. So what we've got is a piece of V-slot extrusion running in V-wheels, which is attached to this. So as I pull this out, the V-slot slides all the way up, and you'll notice this turning, this is a 10-turn pot, which has just got the right diameter, so the 10 turns is pretty much the whole length, and we've got a string that goes around an idler at the other end with a little spring tensioner. As we move this, the end here has got a screw in which is attached to the string, and so that turns the pot round and round. So then we can use that pot to measure the position of this on its full scale with an Arduino analog in. So I've now built a controller with two solenoid valves and an Arduino that's linked to the cylinder, and that's my feedback pot wire. So we've got another feedback pot on here as well, which is going to set the position of the cylinder, and that's read into an analog in as well as the one from the actual cylinder so we can compare them. We've got a relay board here that drives the solenoids. I could use MOSFETs, I just don't have any, so I'm just using two channels there to handle the current for the actual solenoid valves. Right, so I've now connected air. I've got air at about 60 psi, and each of these has actually got a test button on, so if I press this one, it should make the thing shoot out, and you'll see that went quite quickly there. And even if I run that to the end and fully pressurise it and then let go, you can hear when I let go it depressurises and air just comes out of the release there. If I push the other one, it shoots back again. But yeah, quite a few problems positioning that, and obviously when I let go of both it's completely open so I can move this and there's no holding power. Now if I try and pressurise both of these, you'll notice it slowly creeps to one end. And the reason for that is that compressed air is just coming in on this T-piece to both the pressure ports on the solenoids, and so basically the bottom of the cylinder has higher pressure. If you remember me saying, that's a bigger capacity because it doesn't have some of it used up by the bar that has to fit in that end. So this end is higher pressure, it's pushing more force this way, and that's basically pushing the air out of this side, back down the tube, back through the T-piece and into this side, so it's always going to creep that way. So we need some sort of solution for that. So what I should probably do is put two non-return valves on here so air can only go in one direction. It can still come out of the release here, which at the moment goes nowhere when we depressurise that side. But I don't have any of those, so for now I'm just going to separate these out into two different air sources. So I've now got two air sources. We've got the original compressor and the other tank that I showed you at the beginning, and I've charged this tank up from the compressor so they're both roughly the same pressure. I have got another regulator here that I can put onto one of them if we need to balance them, because ideally we need to keep them the same pressure, so we keep the same pressure in either side of the cylinder. Right, so now I can drive each way, of course, from the two separate air sources, but if I press both of them, it pretty much holds its position, and if I wasn't holding these valves I'd be able to grab that and it should be pretty solid because we've got compressed air in both sides of the cylinder. Obviously when I let go it decompresses randomly and you get a little shift, and obviously if I pressurise one and let go of the other, air comes out really quick, so it's going to go really quick and uncontrollably. So the next thing we need to do is restrict the flow somehow, probably on the outputs here. Yes, you've guessed it, it's the professional flow restrictors, which basically stop air coming out of the release, and the plan is to let air out slower than it goes in, which means we should be able to maintain pressure in each side of the cylinder. Right, so then I should be able to pressurise both sides of the cylinder, and when I release one, it should move under control in each direction. So that's both of them pressurised and it locked in position, and if I release the left-hand one, it should move slowly, only letting air out very slowly to the left there and hold position when I lock it again, and the same in the other direction. It's quite noisy, the air coming out, but anyway. And of course when I've got them both on, I've got air pressurised in both sides of the cylinder, so it should be holding that cylinder pretty solidly. Again, my hand's on here and I can't tell, but next we're going to activate it all from the Arduino. So I've written some pretty simple Arduino code. Essentially we're reading two variables with analog ins, which are the feedback pot and the input pot, and we've defined two pins there for the relay valves, which are output pins. Now the relay board is active low, so to start with we've turned both of those on by bringing the pins low, which of course pressurises both sides of the cylinder. I've got a serial set up here so that I can print the values out to look at them, but we don't really need that. So we're reading both of those variables into the analog ins. Then it's very simple, it's a very simple if statement. So it basically uses that threshold, and depending on which value is bigger, it turns off one of those cylinders. And if basically it's in the middle, it turns both those pins low, which turns on the cylinders to keep pressure. So the default is that both solenoids are on, and that should be held in position. And now if I turn the knob, it should track with that dead spot to wherever I turn it. So some pressure imbalance in either side of the cylinder due to the two tanks at the moment. But it seems alright, it seems not too bad. I could tune that threshold down, but I don't want it to sit there trying to get to an impossible accuracy. So that's not too bad, and obviously it's held with both solenoids on when I let go. So if I grab this now, it's got some holding power, and it tries to correct if I push it too far and put it back to where it should be. So obviously we've got quite a lot of air though going back down the tube and into the tanks, so it's not that solid. I can move it, but I'm compressing and decompressing air all the way back down into the reservoirs, so that's the reason. If we had the non-return valves here, it'd be much shorter, and so it'd be much harder to move this. But the holding power there is pretty satisfactory. It's better than when the cylinder's open, of course. And just to clarify, the default is both of these are on. You can see the LEDs here for both solenoids. Each one's actually got an LED on. You can maybe just see there. And when I turn it one way or the other, it just turns one off. So air comes in through this one, and it's let out of this one much more slowly through that flow restrictor. So the dead spot is both of them on for holding power, and one off in either direction. So also I can't control the speed. The only way I could make it go faster or slower would be to unclamp or clamp these up some more. So that's something to think about in the future. Perhaps we can make a proportional valve with a motor that turns a clamp and restricts the flow, because then we could do acceleration and deceleration curves. So that worked pretty much as well as I expected it to for the hacky setup that we've got here. Obviously the things to resolve are going to be two non-return valves, so we can feed both sides of the cylinder from the same pressure from the same tank, and also so that we don't recompress the air in the tank all the way back down the tube and into a massive reservoir when we try and backdrive the cylinder, which should make it a lot more rigid. It'd also be good to build some proportional valves that I'm going to experiment with in another video, probably made of servos and some plumbing accessories, and then we can try and do acceleration and deceleration and basically control that speed as well. So I hope you've enjoyed that. Let me know what I should do with these cylinders. Should we make a giant robot that can walk along? If we've got acceleration and deceleration and proportional speed, it can move really well. So hopefully it won't be big and overwhelming. Thanks again to Squarespace for sponsoring this video. Squarespace can provide websites, domains and online shops. Don't forget to use the link in the description to this video to get 10% off. That's squarespace.com/James Bruton. Alright, that's all for now.